The syntax of the Python programming language is the set of rules that defines how a Python program will be written and interpreted. Python was designed to be a highly readable language. It has a relatively uncluttered visual layout and uses English keywords frequently where other languages use punctuation. Python aims towards simplicity and generality in the design of its syntax, encapsulated in the mantra "there should be only a euro, and preferably only a euro obvious way to do it," from the Zen of Python. This mantra is deliberately opposed to the Perl and Ruby mantra, "there's more than one way to do it." Keywords. Python has the following keywords or reserved words. They cannot be used as identifiers. Notes. Indentation. Python uses whitespace to delimit program blocks, following the offside rule. Its uncommon block marking convention is a feature that many programmers, otherwise unfamiliar with Python, have heard of. Python borrows this feature from its predecessor ABC. Instead of punctuation or keywords, it uses indentation to indicate the run of a block. In so-called free-format languages, that use the block structure derived from ALGOL, blocks of code are set off with braces or keywords. In most coding conventions for these languages, programmers conventionally indent the code within a block, to visually set it apart from the surrounding code. Consider a function, foo, which is passed a single parameter, x, and if the parameter is 0 will call bar and baz, otherwise it will call qux, passing x, and also call itself recursively, passing x1 as the parameter. Here are implementations of this function in both C and Python. Foo function in C with k and r indent style. Foo function in Python. Python mandates a convention that programmers in ALGOL-style languages often follow. Moreover, in free-form syntax, since indentation is ignored, good indentation cannot be enforced by an interpreter or compiler. Incorrectly indented code can be understood by human reader differently than does a compiler or interpreter. For example, misleading indentation in C. This code was intended to call functions a and b 20 times. However, the iterated code block is just a. The code calls a 20 times, and then calls b and c only one time each. Later readers of the code may be fooled by the misalignment of the calls to functions b and c. Both space characters and tab characters are currently accepted as forms of indentation in Python. Since many tools do not visually distinguish them, mixing spaces and tabs can create bugs that take specific efforts to find. Moreover, formatting routines which remove hit €, for instance, many Internet forums €, can destroy the syntax of a Python program, whereas a program in a bracketed language would merely become more difficult to read. Many popular code editors handle Python's indentation conventions seamlessly, sometimes after a configuration option is enabled. Data structures. Since Python is a dynamically typed language, Python values, not variables, carry type. This has implications for many aspects of the way the language functions. All variables in Python hold references to objects, and these references are passed to functions. A function cannot change the value of variable references in its calling function. Some people have called this parameter passing scheme call by object reference. An object reference means a name, and the passed reference is an alias, that is a copy of the reference to the same object, just like in C++. The object's value may be changed in the called function with the alias, for example. Function mfunc changed the value of a list with the formal argument al, which is an alias of a list. However, any attempt to operate on the alias itself will have no effect on the original object. In Python, non-innermost local and not declared global accessible names are all aliases. Among dynamically typed languages, Python is moderately type-checked. Implicit conversion is defined for numeric types, so one may validly multiply a complex number by a long integer without explicit casting. However, there is no implicit conversion between numbers and strings. A string is an invalid argument to a mathematical function expecting a number. Base types. Python has a broad range of basic data types. Alongside conventional integer and floating point arithmetic, It transparently supports arbitrary precision arithmetic, complex numbers, and decimal floating point numbers. Python supports a wide variety of string operations. Strings in Python are immutable, so a string operation such as a substitution of characters, that in other programming languages might alter a string in place, returns a new string in Python. Performance considerations sometimes push for using special techniques in programs that modify strings intensively, such as joining character arrays into strings only as needed. Collection types. One of the very useful aspects of Python is the concept of collection types. In general, a collection is an object that contains other objects in a way that is easily referenced or indexed. Collections come in two basic forms: sequences and mappings. The ordered sequential types are lists, tuples, and strings. All sequences are indexed positionally, and all but strings can contain any type of object, including multiple types in the same sequence. Both strings and tuples are immutable, making them perfect candidates for dictionary keys. Lists, on the other hand, are mutable. Elements can be inserted, deleted, modified, appended, or sorted in place. Mappings, on the other hand, are unordered types implemented in the form of dictionaries which map a set of immutable keys to corresponding elements. For example, one could define a dictionary having a string toast mapped to the integer 42 or vice versa. The keys in a dictionary must be of an immutable Python type, such as an integer or a string, because under the hood they are implemented via a hash function. This makes for much faster lookup times, but requires keys not change. Dictionaries are also central to the internals of the language as they reside at the core of all Python objects and classes. The mappings between variable names and the values which the names reference are stored as dictionaries. Since these dictionaries are directly accessible, metaprogramming is a straightforward and natural process in Python. A set collection type was added to the core language in version 2.4. A set is an unindexed, unordered collection that contains no duplicates, and implements set theoretic operations such as union, intersection, difference, symmetric difference, and subset testing. There are two types of sets, set and frozen set, the only difference being that set is mutable and frozen set is immutable. Elements in a set must be hashable and immutable. Thus, for example, a frozen set can be an element of a regular set whereas the opposite is not true. Python also provides extensive collection manipulating abilities such as built-in containment checking and a generic iteration protocol. Object system. In Python, everything is an object, even classes. Classes, as objects, have a class, which is known as their metaclass. Python also supports multiple inheritance and mixins. The language supports extensive introspection of types and classes. Types can be read and compa-reader types are instances of type. The attributes of an object can be extracted as a dictionary. Operators can be overloaded in Python by defining special member functions. For instance, defining add on a class permits one to use the plus operator on members of that class. Literals, strings. Python has various kinds of string literals. Normal string literals, either single or double quotes, can be used to quote strings. Unlike in Unix shell languages, Perl or Perl-influenced languages such as Ruby or Groovy, single quotes and double quotes function identically, that is, there is no string interpolation of $foo expressions. However, interpolation can be done using the %string format operator. For example, the Perl statement is equivalent to the Python statement. However, the current standard for this sort of string formatting is to use the format method of strings. Multi-line string literals. There are also multi-line strings, which begin and end with a series of 3 single or double quotes and function like here documents in Perl and Ruby. A simple example with variable interpolation is raw strings. Finally, all of the previously mentioned string types come in raw varieties, which do no / interpolation and hence are very useful for regular expressions. Compare at quoting in C. Raw strings were originally included specifically for regular expressions. Due to limitations of the tokenizer, raw strings may not have a trailing \. Creating a raw string holding a Windows path ending with a backslash requires some variety of workaround. Examples include concatenation of adjacent string literals appearing contiguously and only separated by whitespace, are allowed and are aggregated into a single longer string. Thus, is equivalent to. Numbers, numeric literals in Python are of the normal sort, for example 0, -1, 3.4, 3.5 -8. Python has arbitrary length integers and automatically increases the storage size as necessary. Prior to Python version 3, there were two kinds of integral numbers, traditional fixed-size integers and long integers of arbitrary range. The conversion to long integers was performed automatically when required, and thus the programmer usually didn't have to be aware of the two integral types. In newer language versions the fixed-size integers are completely gone. Python supports normal floating-point numbers, which are created when a dot is used in a literal, when an integer and a floating-point number are used in an expression, or as a result of some mathematical operations. Python also supports complex numbers natively. Complex numbers are indicated with a j or j suffix, for example 3 plus 4j. Lists, tuples, sets, dictionaries. Python has syntactic support for the creation of container types. Lists are mutable sequences of items of arbitrary types, and can be created either with a special syntax or using normal object creation. Tuples are immutable sequences of items of arbitrary types. There is also a special syntax to create tuples. Although tuples are created by separating items with commas, the whole construct is usually wrapped in parentheses to increase readability. An empty tuple is denoted by. Sets are mutable containers of items of arbitrary types. The items are not ordered, but sets support iteration over the items. A syntax for set creation appeared in Python 2.7/3.0. In earlier Python versions, sets would be created by calling initializing the set class with a list argument. Python sets are very much like mathematical sets, and support operations like set intersection and union. Python also features a frozen set class for immutable sets. Dictionaries are mutable mappings tying keys and corresponding values. Python has special syntax to create dictionaries. The dictionary syntax is similar to the set syntax, the difference is the presence of colons. The empty literal results in an empty dictionary rather than an empty set, which is instead created using the non-literal constructor, set. Operators, arithmetic, Python includes the plus, slash, %, and operators, with their usual mathematical precedence. Traditionally, x/y performed integer division if both x and y were integers, and returned a float if either was a float. However, because Python is a dynamically typed language, it was not always possible to tell which operation was being performed, which often led to subtle bugs. For example, with a call to mean, 3.0, 4.0 would return 3.5, but mean, 3, 4, would return 3. If this was not the intended behavior, it was necessary to use a workaround such as. To avoid this issue, a proposal was made to change the behavior of the Python division operator. In Python 2.2, a new operator was introduced for floor division, both for integer and floating point arguments. The slash operator was changed so that the quotient of two integers returned a float, but for backwards compatibility, this behavior had to be explicitly requested until Python 3.0. Comparison operators, the basic comparison operators such as equals, and so forth are used on all manner of values. Numbers, strings, sequences, and mappings can all be compared. Although disparate types are defined to have a consistent relative ordering, this is considered a historical design quirk and will no longer be allowed in Python 3.0. Chained comparison expressions such as A, B, C have roughly the meaning that they have in mathematics, rather than the unusual meaning found in C and similar languages. The terms are evaluated and compared in order. The operation has short-circuit semantics, meaning that evaluation is guaranteed to stop as soon as a verdict is clear. If A, B is false, C is never evaluated as the expression cannot possibly be true anymore. For expressions without side effects, A, B, C is equivalent to A, B and B, C. However, there is a substantial difference when the expressions have side effects. A, F, X, B will evaluate F, X, exactly once, whereas A, F, X, and F, X, B will evaluate it twice if the value of A is less than F, X, and once otherwise. Logical operators, Python 2.2 and earlier does not have an explicit Boolean type. In all versions of Python, Boolean operators treat zero values or empty values such as 0, none, 0.0, and as false, while in general treating non-empty, non-zero values as true. In Python 2.2.1 the Boolean constants true and false were added to the language. The binary comparison operators such as and return either true or false. The Boolean operators and or use minimal evaluation. For example, y0 or xy greater than 100 will never raise a divide by zero exception. Note that these operators return the value of the last operand evaluated, rather than true or false. Thus the expression evaluates to 5, and evaluates to 4. Functional programming, as mentioned above, another strength of Python is the availability of a functional programming style. As may be expected, this makes working with lists and other collections much more straightforward. List comprehensions. One such construction is the list comprehension, which can be expressed with the following format. Using list comprehension to calculate the first 5 powers of 2. The quicksort algorithm can be expressed elegantly using list comprehensions. First-class functions. In Python, functions are first-class objects that can be created and passed around dynamically. Python's limited support for anonymous functions is the lambda construct. Since the availability of full anonymous functions is non-existent, the main use for lambda functions is named functions. Lambdas are limited to containing expressions rather than statements, although control flow can still be implemented less elegantly within lambda by using short-circuiting. Closures. Python has had support for lexical closures since version 2.2. Here's an example. Python's syntax, though, sometimes leads programmers of other languages to think that closures are not supported. Variable scope in Python is implicitly determined by the scope in which one assigns a value to the variable, unless scope is explicitly declared with global or non-local. Note that the closures binding of a name to some value is not mutable from within the function. Given. You can see that b, as visible from the closure scope, retains the value it had. The changed binding of b inside the inner function did not propagate out. The way around this is to use a mutable value and change that value, not the binding. For example, a list with one element. Generators, introduced in Python 2.2 as an optional feature and finalized in version 2.3, generators are Python's mechanism for lazy evaluation of a function that would otherwise return a space-prohibitive or computationally intensive list. This is an example to lazily generate the prime numbers. To use this function simply call, for example. The definition of a generator appears identical to that of a function, except the keyword yield is used in place of return. However, a generator is an object with persistent state, which can repeatedly enter and leave the same scope. A generator call can then be used in place of a list, or other structure whose elements will be iterated over. Whenever the for loop in the example requires the next item, the generator is called, and yields the next item. Generators don't have to be infinite like the prime number example above. When a generator terminates, an internal exception is raised which indicates to any calling context that there are no more values. A for loop or other iteration will then terminate. Generator expressions. Introduced in Python 2.4, generator expressions are the lazy evaluation equivalent of list comprehensions. Using the prime number generator provided in the above section, we might define a lazy, but not quite infinite collection. Most of the memory and time needed to generate this many primes will not be used until the needed element is actually accessed. Unfortunately, you cannot perform simple indexing and slicing of generators, but must use the iter tool's modules or roll your own loops. In contrast, a list comprehension is functionally equivalent, but is greedy in performing all the work. The list comprehension will immediately create a large list, even if most elements are never accessed. The generator comprehension is more parsimonious. Dictionary and set comprehensions, while lists and generators had comprehensions expressions, in Python versions older than 2.7 the other Python built-in collection types had to be clutched in using lists or generators. Python 2.7 and 3.0 unify all collection types by introducing dict and set comprehensions, similar to list comprehensions. Objects. Python supports most object-oriented programming techniques. It allows polymorphism, not only within a class hierarchy but also by duck typing. Any object can be used for any type, and it will work so long as it has the proper methods and attributes. And everything in Python is an object, including classes, functions, numbers and modules. Python also has support for metaclasses, an advanced tool for enhancing classes functionality. Naturally, inheritance, including multiple inheritance, is supported. It has limited support for private variables using name mangling. See the classes section of the tutorial for details. Many Python users don't feel the need for private variables, though. The slogan "We're all consenting adults here" is used to describe this attitude. Some consider information hiding to be unpythonic, in that it suggests that the class in question contains unaesthetic or ill-planned internals. However, the strongest argument for name mangling is prevention of unpredictable breakage of programs. Introducing a new public variable in a superclass can break subclasses if they don't use private variables. From the tutorial, as is true for modules, classes in Python do not put an absolute barrier between definition and user, but rather rely on the politeness of the user not to break into the definition. OOP doctrines such as the use of accessor methods to read data members are not enforced in Python. Just as Python offers functional programming constructs but does not attempt to demand referential transparency, it offers an object system but does not demand OOP behavior. Moreover, it is always possible to redefine the class using properties so that when a certain variable is set or retrieved in calling code, it really invokes a function call, so that spam eggs equals toast might really invoke spam set eggs, toast. This nullifies the practical advantage of accessor functions, and it remains OOP because the property X becomes a legitimate part of the object's interface. It need not reflect an implementation detail. In version 2.2 of Python, new style classes were introduced. With new style classes, objects and types were unified, allowing the subclassing of types. Even entirely new types can be defined, complete with custom behavior for infix operators. This allows for many radical things to be done syntactically within Python. A new method resolution order for multiple inheritance was also adopted with Python 2.3. It is also possible to run custom code while accessing or setting attributes, though the details of those techniques have evolved between Python versions. With statements, the with statement handles resources. One function is called when entering scope and another when leaving. This prevents forgetting to remove the resource and also handles more complicated situations such as exceptions. Properties. Properties allow specially defined methods to be invoked on an object instance by using the same syntax as used for attribute access. An example of a class defining some properties is descriptors, a class that defines one or more of the special methods get, self, instance, owner, set, self, instance, value, delete, self, instance, can be used as a descriptor. Creating an instance of a descriptor as a class member of a second class makes the instance a property of the second class. Class and static methods. Python allows the creation of class methods and static method via the use of the atClass method and atStatic method decorators. The first argument to a class method is the class object instead of the self-reference to the instance. A static method has no special first argument. Neither the instance, nor the class object is passed to a static method. Exceptions. Python supports exception handling as a means of testing for error conditions and other exceptional events in a program. Indeed, it is even possible to trap the exception caused by a syntax error. Python style calls for the use of exceptions whenever an error condition might arise. Rather than testing for access to a file or resource before actually using it, it is conventional in Python to just go ahead and try to use it, catching the exception if access is rejected. Exceptions can also be used as a more general means of non-local transfer of control, even when an error is not at issue. For instance, the Mailman mailing list software, written in Python, uses exceptions to jump out of deeply nested message handling logic when a decision has been made to reject a message or hold it for moderator approval. Exceptions are often used as an alternative to the if block, especially in threaded situations. A commonly invoked motto is EAFP, or it is easier to ask for forgiveness than permission, which is attributed to Grace Hopper. In this first code sample, there is an explicit check for the attribute. This second sample follows the EAFP paradigm. These two code samples have the same effect, although there will be performance differences. When spam has the attribute eggs, the EAFP sample will run faster. When spam does not have the attribute eggs, the EAFP sample will run slower. The Python profiler can be used in specific cases to determine performance characteristics. If exceptional cases are rare, then the EAFP version will have superior average performance than the alternative. In addition, it avoids the whole class of time of check to time of use vulnerabilities, other race conditions, and is compatible with duck typing. A drawback of EAFP is that it can be used only with statements. An exception cannot be caught in a generator expression, list comprehension, or lambda function. Comments and docstrings. Python has two ways to annotate Python code. One is by using comments to indicate what some part of the code does. Single-line comments begin with the hash character and are terminated by the end of line. Comments spanning more than one line are achieved by inserting a multi-line string that is not used in assignment or otherwise evaluated, but sits in between other statements. Commenting a piece of code. Commenting a piece of code with multiple lines. Docstrings, that is, strings that are located alone without assignment as the first indented line within a module, class, method or function automatically set their contents as an attribute named doc, which is intended to store a human-readable description of the object's purpose, behavior, and usage. The built-in help function generates its output based on doc attributes. Such strings can be delimited with, or for single-line strings, or may span multiple lines if delimited with either or, which is Python's notation for specifying multi-line strings. However, the style guide for the language specifies that triple-double quotes are preferred for both single and multi-line docstrings. Single-line docstring. Multi-line docstring. Docstrings can be as large as the programmer wants and contain line breaks. In contrast with comments, docstrings are themselves Python objects and are part of the interpreted code that Python runs. That means that a running program can retrieve its own docstrings and manipulate that information. But the normal usage is to give other programmers information about how to invoke the object being documented in the docstring. There are tools available that can extract the docstrings to generate an API documentation from the code. Docstring documentation can also be accessed from the interpreter with the help function, or from the shell with the pydoc command pydoc. The doctest standard module uses interactions copied from Python shell sessions into docstrings to create tests. Function annotations. Function annotations are defined in PEP 3107. They allow attaching data to the arguments and return of a function. The behavior of annotations is not defined by the language, and is left to third-party frameworks. For example, a library could be written to handle static typing. Decorators. A decorator is any callable Python object that is used to modify a function, method or class definition. A decorator is past the original object being defined and returns a modified object, which is then bound to the name in the definition. Python decorators were inspired in part by Java annotations, and have a similar syntax. The decorator syntax is pure syntactic sugar, using it as the keyword. Is equivalent to. Decorators are a form of metaprogramming. They enhance the action of the function or method they decorate. For example, in the above sample, Viking chorus might cause menu item to be run 8 times for each time it is called. Canonical uses of function decorators are for creating class methods or static methods, adding function attributes, tracing, setting pre- and post conditions, and synchronization, but can be used for far more besides, including tail recursion elimination, memoization and even improving the writing of decorators. Decorators can be chained by placing several unadjacent lines. Is equivalent to. Or, using intermediate variables. In the above example, the favorite color decorator factory takes an argument. Decorator factories must return a decorator, which is then called with the object to be decorated as its argument. This would then decorate the black knight function such that the color, blue, would be printed prior to the black knight function running. Closure ensures that the color argument is accessible to the innermost wrapper function even when it is returned and goes out of scope, which is what allows decorators to work. In Python prior to version 2.6, decorators apply to functions and methods, but not to classes. Decorating a new method can modify a class, however. Class decorators are supported starting with Python 2.6. Despite the name, Python decorators are not an implementation of the decorator pattern. The decorator pattern is a design pattern used in statically typed object-oriented programming languages to allow functionality to be added to objects at runtime. Python decorators add functionality to functions and methods at definition time, and thus are a higher-level construct than decorator pattern classes. The decorator pattern itself is trivially implementable in Python, because the language is duck-typed, and so is not usually considered as such. Easter eggs. Users of curly bracket programming languages, such as C or Java, sometimes expect or wish Python to follow a block delimiter convention. Brace delimited block syntax has been repeatedly requested, and consistently rejected by core developers. The Python interpreter contains an Easter egg that summarizes its developers' feelings on this issue. The code from future import braces raises the exception syntax error, not a chance. The future module is normally used to provide features from future versions of Python. Another hidden message, the Zen of Python, is displayed when trying to import this. The message "Hello World" is printed when the import statement import hello is used. In Python 2.7, instead of Hello World, it prints Hello World. An anti-gravity module was added to Python 2.7 and 3.0. Importing it opens a web browser to an XKCD comic that portrays a humorous fictional use for such a module, intended to demonstrate the ease with which Python modules enable additional functionality. References. External links. Python tutorial written by the author of Python, Guido van Rossum.